Everyone, this is Lee here. In this video, we are going to go over a practice problem for the projectile motion unit. All right, let's begin. So in front of you, you should see a basic projectile motion practice problem. If you're able to solve this, you could basically solve any kind of projectile motion problem. They might throw you like a couple of curveballs here and there, but this is the basic idea. Okay, so here it says a object is launched at a velocity of 20 meters per second in a direction making an angle of 25 upwards with the horizontal. And we have to solve it for different parts, A, B, C, and D. Now, what I suggest that you do is you should always start off with a drawing. Oops. And the reason why you should always start off with a drawing is because you can write on the drawing and you can have very important ideas on that drawing. So we have an object here, and it is launched with a velocity of 20 meters per second. So boom, 20 meters per second. We can call that V initial. And it is launched at an angle of theta, which is going to be 25 degrees. All right, and then it's going to go pew. I'm just going to land somewhere over there. Okay, and trust me when I say the sound effects do help. All right, it says what is the maximum height reached by the object? Okay, so if I'm solving for maximum height, so let's write that down here, a height. So I'm looking at this part right there, is peak. Now this is what I know. Height, if you remember from the other video, it's a y variable. Okay, height is a y variable. So we need to be solving for the problem using our y variables and our y variables only. So I'm going to create my kinematics table. All right, so instead of saying XO, I'm going to say YO because we are along the y-axis. So V initial Y, V final Y, A sub Y, and time. All right. Now, once again, hopefully you drew the diagram, and we're going to say here that's the peak. Because whenever I see a picture, and there's something I need to remember from the picture, seeing the picture, it really helps. So let's go over through this. We know that we started off the ground, so our height is going to be 0. Okay, our y final, that's our question mark. We don't know what that is. We're trying to solve it. Our v initial y, we know this. Okay, so I'm going to do a little sidebar over here. So if we have an object that's moving with 20 meters per second, and this is our angle theta, okay, we need to create our x and y components. Our VOY is over here, and if I take a look at the angle, I can see that this angle and VOY, it is opposite of each other. And because it's opposite, we're going to use sine. So we can say that it is going to be V initial sine of theta, which is 20, which is the hypotenuse, sine of the angle, and I believe this was 25 degrees. Okay, 25 degrees. All right. And so I'll put that in right there. So 20 sine of 25. Now, just as a little caveat, when we do physics here, we have to be in degree mode, okay, and not radian. Radian is a no-go for us. All right, we cannot use radians. Degree mode only, please. So if you're using your calculator, if you're using an online calculator, make sure you check the mode to be in degrees. All right, now VFY, this is why I'm saying drawing really helps, because if I take a look at this and I'm like, oh, I remember, if I take a look at this path, notice that at the peak, it's not going up or down. It's pretty flat up there. And that's just a great reminder for that. At the peak, our velocity is 0 meters per second. Our acceleration is negative 10 meters per second squared, and we have to find our time, maybe? Who knows, right? So we have all of this information, and where do we go next? You guessed it, the kinematics equations. All right, so what I'm going to do is off on the side, I'm going to write out the kinematics equations for us. We have xf is equal to xo plus v initial t plus 1/2 at squared. Now, you don't have to have these memorized. You will have access to the equation sheet, but I just, oops, that should be a t, but I didn't have that available for us, and so I'm just quickly jotting it down to a xf minus xo. Okay, so strategy is the same. I am trying to find my final position. Now I know here in the equation sheet it has it as x, but that's just same position. And because we're talking about y position, we can imagine that xf being actually a yf. Okay, so if I take a look at the first one, all right, it has a missing variable. I'm going to check to make sure all the other things are filled in. So do I have xo? Yes. Do I have v initial? Oh, yes I do. Do I have time? No, I do not. Okay, now because I don't have the time variable over here, I can't use the first one. All right, if I take a look at the second equation doesn't even have the final position. I can't even use that one. All right, what about this one? All right, do we have final velocity? Yes, I do. Do I have initial velocity? Yes, I do. Do I have the acceleration? Yes, I do. Do I have final position? Yes, I do. It's a question mark. Do I have my initial position? Yes, I do. All right, and so I would use that equation to fill in and find my y final. And if you do that properly, looks like, what did they get? It should be roughly around 3.64 meters. So I'm going to say roughly around 3.64 meters. My answer key used negative 9.8 instead of negative 10. And so if you get a number like, I think probably like 3.7-ish, 3.7, 3.8-ish, you know you're on the right track, okay, from using this equation. All right, next up. What is the total flight time between launch and touching the ground of the object? All right, so total flight time. It looks like we can probably use this table here, okay, the y table, because remember what I said, usually the y table helps us with finding the time. So I'm going to create another table because this is for a different problem, right? Now, here's something cool. So we know our initial position and our final position is going to be, let's see, both are 0. Excuse me. Our initial y will be 20 sine of 25, and because it's landing at the same height, the final velocity will just be a negative version of that. Your acceleration should be like negative 10 meters per second squared, and we're looking for the time. All right, so ignoring everything up here, because those are just zeros, here is everything that we can now fill in. We basically have an entire chart. So I'm going to take a look at my equations, right? Let's see if I can use my first equation. Do I have final position? Yes. Do I have my initial position? Do I have my final position? Yes. Initial position? Yes. Initial velocity? Yes. Time? No, but it's what we're looking for. Acceleration? Yes. And time. All right, so we could probably use the first equation there. But just in case, let's take a look at the other ones. Do I have final velocity? Yes. Initial velocity? Yes. Acceleration? Yes. Time? Yes. All right, so we could even use the second one. Do I have final velocity? Yes. Initial velocity? Yes. Acceleration? Yes. XF and XO? Yes and yes, but I want to point out something. Your final position and your initial position are both 0, and so everything multiplied will be 0. And if everything is multiplied by 0, this all becomes 0. Like 0 is all around, so we can't actually use this one. But I'm going to use the second one. Primarily because it's got the least amount of writing and stuff, and so we're going to use the second equation to solve for the total time. So we have VF, VO plus AT. We have negative 20 sine 25 is equal to 20 sine 25 plus negative 10t. I'm going to subtract 20 sine 25 over on the other side. So we get negative 40 sine 25 is equal to negative 10t. T is equal to negative 40 sine of 25, all divided by negative 10. So we get 4 sine of 25, whatever that is. And according to the answer key, that should be right around 1.72 seconds. Okay. All right. So right around. They use 9.8, and so ours might be a little bit higher than that. All right. On a roll. C, what is the horizontal range, maximum x, of the object? Okay, now this is where things get cool. So up until now, we only use the y variables. Now we can use our x stuff. We're talking about range. So we have XO, we have XF, we have VO, we have VF, we have A sub x, and we have T. All right, so we have all this. Okay, and so because we have all that, we can fill it in, right? We know our initial position is 0. We know our final position is what we're looking for. That's our range, our initial v velocity. All right, so we got to think about this. If we use sine for the y-axis, we can use cosine for the x-axis. So it'll be VO cosine 25, and because the initial and the final are the same, we say that the two are equal. A sub x is going to be 0. Okay, that's usually the case in the x-axis unless told otherwise. And we found what t was from before, 1.72. So I'm going to put that in there, 1.72 seconds. All right. Now, same as always, you're going to look to the kinematic equations to see which equation we need. Okay, we need whatever one doesn't give out all zeros, and the one with the missing variables. And so if I take a look here, we try to, let's see if I can clean this up a little bit. There we go. All right, so cleaned up a little bit. There we are. Make this easier for us to see. Okay, gonna go through variable by variable. All right, xf is what we're looking for. XO is what we have. We have the initial, we have time, we have acceleration. In fact, it's 0, so that really cleans things up for us. And therefore, we have the equation that we can use. We can use the first one. All right, so if we use the first equation, which is xf is equal to xo plus v initial t plus 1/2 at squared. Hopefully you can find the, you gotta plug it in, and you should find the x of f right around 31.26 meters. And once again, this was using negative 9.8, so yours might be a little bit higher if you use 10, just like me. All right, so we're almost there. Last one. What is the magnitude of the velocity of the object just before it hits the ground? Wowee zowie. Now, you might be thinking to yourself, ooh, how do we get that? Now, I'll just tell you this. This one is more of a conceptual problem, okay? Because it's hitting the ground, and the ground is where it got launched, this one's a little bit easier than it might seem. Because if we use our ideas and our concepts, we know that this object launched at 20 meters per second, and it was going up and to the right, okay? So if it's hitting the ground, it needs to hit the ground with the same velocity. And not only that, but it actually hits the ground with the same direction as well. And so our answer would be, it hits the ground at 20 meters per second with 25 degrees to the horizontal. Okay, so it'll be negative 25. And so what that means is that when it hits the ground over here, okay, so if I were to magnify that, right, so this is the ground, right, that's my ball, it would hit the ground like so, and my axes would look something like this, or my components. Right, where this is my theta, and that will be 25. Now, how you can find this, okay, how you can find this is using a trig identity. So I'm going to take this triangle, and I'm going to include this triangle over here. So we have the, right, so we got something that looks like this. We know this is the angle. So this is what we know. We know that this is v sub x final. We have this as v sub y final, and this is just v sub f. In order to find the actual v sub f, right, if you have v of x and v of y, you can solve for v of f using the Pythagorean theorem. Now, to find the angle, okay, you got to use the third trig identity that we usually don't use, the TOA. So TOA, which states that the tangent of the angle is equal to opposite over the adjacent side. All right? And because we're looking for the angle, we can say that the angle is equal to the inverse tangent of the opposite side over the adjacent side. And if we're using our terminology over here, the variables that we're using, we will say the inverse tangent is equal to the opposite, which is vfy, divided by vf of x. Okay? And that will give you the angle. Now, be warned that when you plug in vfy over here in our equation, it has to be negative, and that is because the object is going downwards. All right, and if you were to properly do that, where I believe we found both vfx and vfy before, right? We said that vfx was vo cosine of 25. Okay, that was our v of x, and we said our vfy, because it lands with the same, yeah, over here. That's our vfy. It will be negative 20 sine of 25. If we plug that in here, okay, we should get a angle of, dun, da, da. What is our angle? 25 degrees. Okay, with the horizontal. All right. Well, that's that. I'll see you next time. Bye-bye.